Very pleasant morning to all. I hope that you all stay safe and healthy. I am Saravana Kumar, Assistant Professor in the Department of Mechanical Engineering. It is a great pleasure to share a few words about our college and our department. Francis Xavier Engineering College is located at Tirunelveli City and it was established in the year 2000. FX Engineering College comes under SCAT group of institutions. We offer 6 UG programs, 10 PG programs, and have scholars carrying out doctoral studies in our research centers. Our college has achieved many awards. Among all, I would like to list a few to your knowledge. We have got gold category for Industry Linked Technical Institute, which was awarded by AICTE CII survey for 2 consecutive years. In Chronicle Engineering College survey, we achieved third position among 19 engineering colleges in India. In Times Best Engineering College survey, our college has obtained 15th rank in Tamil Nadu and 108th rank in India. The Department of Mechanical Engineering is the largest department on campus with 600 plus students, 35 faculty members, and with good infrastructure facilities. We offer BE in Mechanical Engineering and ME in Industrial Safety Engineering. The UG program is accredited by NBA, the National Board of Accreditation. Our department is permanently affiliated to Anna University. Apart from course-defined curriculum, we offer a number of value-added courses and impart various skill training to the students. In addition to well-equipped laboratories that comes under curriculum, we have a few special labs for encouraging innovation and new product development. We also have a strong academy for training students to appear for GATE exams. Our department has signed many MOU with leading manufacturing and service industries. We also offer international certification program on Fanuc CNC programming, computer-aided design, non-destructive testing, and BMW Hyundai Industry Associated Laboratories. Our students are actively participating in many technical competitions, winning prizes and bring glory to our department. The research area of our faculty members are bioenergy combustion, solar desalination, green manufacturing, waste heat recovery, biomass gasification, and composite materials. We have also organized many international conferences, workshops, and funded seminars. I hope this session will be more useful for all of us. With this introduction, I welcome all the participants for this session. Hope we will have a great learning today. Thank you.
Hello everyone, a very happy morning to all. I am Ram Kumar, Assistant Professor in the Department of Mechanical Engineering. I am very happy in introducing the respectable speaker of today's event, Mr. Prabhu Sundararajan, who was well known for his great knowledge in the field of computer-aided engineering. He did his BE in Mechanical Engineering from Anna University in the year 2005 and later did his master's degree in Computer Integrated Manufacturing from CEG campus Chennai in the year 2008. He started his career as a project engineer in handling projects related to structural analysis and fixed design for major automotive manufacturers like Audi, Mercedes and Volkswagen. After his postgraduate, with his keen interest towards computer-aided engineering, he has been associated with FL Smith as lead engineer in bulk material handling segment for customers like Adani, National Thermal Power Corporations and Utkal etc. Presently, he is working as Senior Manager, Technical Support for South India in Design Tech Systems Private Limited. He has been dynamic in addressing the engineering challenges in terms of finite element analysis and multi-body dynamics. And also, he is expert in implementing CAE solutions into various R&Ds of automotive and defense industries. We are fortunate enough to have such an eminent person as a keynote speaker. And I am sure his lectures will make a very big impact on our knowledge towards industrial design. With this introduction, I welcome Mr. Prabhu Sundararajan sir for this event and I hand over the session to him. Thank you all.
Proceed பண்ணலாமா?
Good morning to all. I am Prabhu Sundararajan, taking care of technical support activity for Altair products. And I thank everybody who has organized this presentation uh, for this simulation driven design. So, basically, simulation driven design is an environment for design engineers, uh, those who can quickly create the concepts, and they can perform the design concepts at the earlier stage of the design cycle. So when I say simulation driven design, it is like putting simulation in front of the design, and using different simulation technology, we are arriving the different concepts. So from the simulation, we are deriving the design. That's why we call it as simulation driven design. So, and the topic what we are going to cover is like I'm going to just give a brief introduction about Altair HyperWorks and ST Inspire, which is a concept design tool. We are going to see with live demo, and also I'm going to give insight about Inspire Cast. Inspire Cast is a casting simulation tool where user can define different casting feasibilities. And also Inspire Form is a sheet metal forming simulation tool, especially for forming simulation. And we have Print 3D is for 3D printing simulation. So coming to Altair, so Altair is founded in 1985, and we have 80,000 plus customers globally, and we have 60,000 plus users across the globe, and 2,500 engineers, scientists, and creative thinkers. And we have 81 offices across 25 countries. So, when I say about the software, Altair software suites, like we have categorized into modeling and visualization, physical solver, simulation driven design, data intelligence, Internet of Things, and high performance computing. So when I say modeling and visualization, Hypermesh. Hypermesh is the powerful preprocessor for finite element modeling, and it is widely used in most of the industries and R&D centers. And Hypercrash is the preprocessor for crash environment. And we have Hyperview. So Hyperview is the post processor, and Hypergraph is the tool for post processing the graphical results in terms of graphs. And Motion View is the tool for preprocessor for multi-body dynamics, and SimLab is the preprocessor for powertrain components, like especially a casting component or kind of complex component. You can use SimLab as a machine tool. So it is a feature-based machine tool where you can capture the features individually and you can generate the mesh. And coming to physical solvers, we have OptiStruct, which is a structural, linear, and non-linear solver. And Radius is an explicit solver, and Flux is a low-frequency electromagnetic solver, and AccuSolve is the computational fluid dynamics solver, and FICO is a high-frequency electromagnetic solver, and we have Motion Solve for multi-body dynamics, and Multi-Scale Designer is for composite material analysis. And coming to simulation driven design environment, we have ST Inspire, especially for concept design, and Inspire Cast for casting feasibility, and Inspire Extrude for extrusion process, and Inspire Form for sheet metal forming. And we have Compose for map modeling, and Activate for 1D simulation, Embed for control systems and code generation. And we have another meshless technology. We call it as completely a meshless technology. So it is same solid, basically. So user can generate, or user can quickly perform the analysis in a shorter time duration with large assemblies. So, and also we have SimLab ST for multiphysics simulation. And apart from that, we have data intelligence and Internet of Things, that is like smart edge, smart core, and smart sites, etc. And also we have high performance computing. And we have more than 170 applications through partner alliance products. So these are our global customers. We have customers across different industries like automotive, aerospace, government sector, heavy engineering, consumer goods, and energy sector, architectural sector, and so on. Now, so as I said, simulation-driven design. So when we say simulation-driven design, so by enabling simulation-driven design, design engineer can create and investigate a structurally efficient and manufacturable concept at the earlier stage of the design cycle. Thereby, they can reduce the tryouts and physical tryouts and the time that is incurred for development of the product. So, ST Inspire is the powerful concept design tool. So, it also has multi-body dynamic simulation, and you can perform different types of optimization like topology optimization, topography optimization, and size optimization, and so on. So how it works. So I'll play a small video that will explain you how Inspire works at the concept design level. So it's solid thinking Inspire. So be it energy sector or heavy engineering or industrial application or architectural design. So the basic layout is like you need to define the kind of baseline design to the model. So based on the baseline design, the software will give you the optimized material distribution based on the loads and boundary condition. So what you're seeing is nothing but the optimized material distribution for the given design space. And this is the a sample problem which has been solved. So it is the existing model we have taken, and we want to reduce the weight of the component. So we have created it as a design space and non-design space. From the topology optimization, we are able to arrive the optimized material distribution. So what you are seeing is nothing but the validation of the optimized material material layout. Post to that, you can basically you can generate it as a surface model by using polymorphs, and that can be imported to CAD modeling too. So what you are seeing is nothing but the complete model which has been generated through polymorphs, and this component has been manufactured and it is in use right now. So so it's a small insight about ST Inspire. So ST Inspire gives the right design at the first time. At the same time, it's a light design, I would say. So when you see the challenges of traditional tool design process, so you have a conceptual stage to the validation stage. So when I take a conceptual stage, the product knowledge will be much lesser at the conceptual stage. When you go to the till validation stage, the product knowledge will be more. As you see, the degree of freedom for design change at the conceptual stage is high, and at the validation stage is low. So especially design in ST Inspire plays the vital role at the conceptual stage in order to derive the optimized design layout. So what you are seeing is the two different approach. One is traditional approach and a optimization driven approach. If you see the traditional approach, first you will generate a CAD model, and the CAD model then it will be transferred to CAE. CAE engineers will perform the analysis and they will give the output to the CAD engineers once again, whatever the modification that need to be done, all and the relevant parameters. But when you take the optimization driven design, the before CAD, you are doing this optimize conceptual stage. That is, Inspire works before the CAD design. Okay, so from the ST Inspire, you will derive the optimized structure that has been given to the CAD model. So from the conceptual design engineer will start build the model, and then it will be transferred to the advanced simulations. So this is the scenario. So it that is the simulation driven design works at the or before the CAD or design process. So benefits of ST Inspire. So basically, you can get upfront concept design, and it is very easy to learn, and it generates a concept in minutes, and also it solves many challenging industrial design problems, and it has interface with all the existing CAD tools. And I'll take a small video. So this video will explain how we can perform the topology optimization. So basically, topology optimization is performed in order to improve the stiffness and stiffness of the component, and also if you want to maximize the frequency of the component, you can use topography optimization. So topography optimization in Inspire, ST Inspire is much faster when compared to uh, what do you say? It is much faster because of the user friendliness, and you can define different parameters like bead patterns and draw directions, and then you can directly run the simulation. So once you run the simulation, the software will give you the optimized bead pattern in order to improve the stiffness of the component. So what you are seeing is the bead pattern that is generated through topography optimization. So this is the bead pattern. So by using the same bead pattern, you can analyze the structure and you can determine the strength of the component. So now you can see the stiffness and frequency level that is generated using Inspire motion. So basically, you can create the joints, you can create the contact, you can apply the different motions on the system, and you can predict the different behavior of the system by using Inspire motion. So it is very user friendly to simulate, and also you can perform transient study and steady state static study, and you can extract the loads that is generated during the mechanism, so which will be useful for designing the component further. Okay. And also you can estimate the torque requirement and also you can perform the flux body simulation. So where you can dynamically study the stress pattern that is generated during the dynamic condition of the simulation and so on. Okay. So this is basically inspired motion. So let me take a sample model and demonstrate you how this Inspire ST Inspire works. So just I want to share my screen, new screen. So I'll take this sample problem. So what you're seeing is it's a kind of automotive bracket where one end is fixed. So we are going to arrest the degrees of freedom at this particular end, and we are going to apply the load on this particular uh, end. And we want to determine what is the optimized material distribution. So optimized material distribution in the sense I want to reduce the weight of the component without compromising the strength. So if you see ST Inspire, it has an option to import multiple models. Like you can see here, you can import IGS, KTR, Ferrosolid, STEP, and ProE, and so on. So different file formats you can import over here, and it has different modules like geometric page for geometrical cleanup option or geometry creation and editing option, and also you have Inspire structure for uh, structural analysis and optimization, and Inspire motion for defining the multi-body dynamics simulation, and also you have Inspire manufacture for casting simulation and forming simulation, and we have Print 3D for what you can say you can perform the 3D printing simulation using this tool. So now I am going to apply the loads and boundary condition. I'm going to structure and I'm selecting the constraints. So here I'm applying translation with respect to x, y, and similarly on the other end, I'm applying like I'm arresting translation with respect to X, Y, and Z direction. And I'm going to apply the load at this end. So I'm going to apply the load for here, like I would say some 14,500 Newton with respect to Z axis. So, so similarly, I'm applying the force on the other side of the component. So you can see here, we have applied the load. Suppose to that, you need to define the material. What type of material is that? So once you select the component, you can see here the material. So user can define their own material as per the standard. So you have different standards over here. And also you need to define the design space. So design space is the region where you want to optimize the material. So I'm selecting this particular part and designating it as design space. So once I designate it as design space, you can see it, the color has been changed to brown. So now we can run the optimization study. So you can click on optimization. So once you click on optimization, you can see here there are different optimization techniques available: topology, topography, gauge optimization, and lattice structure optimization, and so on. And then you need to define the objective. What is your objective? Whether you want to maximize the stiffness, or you want to minimize the mass, or you want to maximize the frequency. So that you need to define. I'm selecting maximizing stiffness. And then you need to define the mass target. What is your mass target? So that you need to define. And also you can define your manufacturing constraint like minimum thickness, maximum thickness, and so on. So once you define all this parameter, you can directly run the simulation. So uh, I'll show you the result after running the simulation. So this is the result that is we got after running the simulation. So no. So you can see here, initially we got the material layout like this. So the software says these are the region where you need to retain the material. The remaining region you can remove the material. So this material distribution is arrived based on the load path that is derived from the structural analysis, and so this can be saved as a CAD model, and you can use it in your CAD tool for further design fine tuning and so on. So, and one more thing, what we can do is we can define the design constraints in order to make the material that is optimized structure into a manufacturable concept. So there is an option called shape control. So by using shape control, you can give the different types of manufacturing constraints. Like you can define single draw, split draw, extrusion, overhang, and so on. So after defining this, you will get a material distribution like this, which is manufacturable. Okay. So this is how. So the same design can be saved as a CAD model, and then you can use it for your design fine tuning purpose. Okay. So let me move to the presentation. So that's all about Inspire structure. Then we are going to see about Inspire Cast. As I said, Inspire Cast is the casting simulation tool which helps the design engineer to perform the casting feasibility study, and also it allows the user to determine the potential casting defects at the earlier stage of the design cycle. So user can determine the defects such as air entrapment, shrinkage porosity, cold shed, mold degeneration, and they can rectify those defects at the earlier stage to avoid the costliest downstream correction. So ST Inspire has a guided template basically for different types of casting simulation process. So as I said, it is fast and easy, accurate, affordable framework, and with 5 simple steps, you can perform the casting simulation process. So there are different types of casting simulation process that we can perform using Inspire Cast, or like you have high pressure die casting, you have low pressure die casting, you have investment casting, and also you can perform sand casting and so on. When I say geometry creation capabilities, it has intuitive geometry creation toolbars so that you can create the most of the secondary components of the casting, and also you can create mold and core in a single click. So that is possible. Apart from that, it has a full control on creation of risers, and you can manipulate the size of the riser, and you can adjust the position of the riser and so on. It has a guided template for most of the casting simulation process. So all the casting simulation process will have a proper guided template. It's a 5 step simulation workflow. I'll play a small video that will explain you the like what are the steps that has been involved while we performing the casting simulation process. So just I'll play this video. Yeah. So first you can import the CAD model. So after importing the CAD model, you can define the type of material of the casting part, and also you can define the gating system, right? Uh, Runner system or gating system and so on. And also you can adjust and orient the position of the gating system uh, just by using manipulator toolbar. So once you're done with that, you can extract the core part. So that is also possible. You can directly extract the core part using an option called core. So that is available in component toolbar. So once you extract the core, the software will allow you to adjust further. So you can do further modification on the core in order to the requirement of the casting simulation process. And then you can create the riser. As I said, you have full control of dimensioning the riser. So you can adjust the section modulus, or you can adjust the diameter of the riser, and so on. So that's what we are doing here. So just we are adjusting the dimension of the riser. Once you've done that, you can create the mold. So within single click, you can create the mold, and then you can run the simulation. So you can set up what type of analysis is that, like whether it is high pressure die casting or low pressure die casting or investment casting. That you can set, and then you can directly run the simulation. So this is the simple 5 step workflow. So coming to output that we derive from the analysis, or like filling, front flow, and also you can determine the velocity, temperature, and pressure distribution across the component, air entrapments, and cold sheds. So where you can identify the metal building of the metal, all those things you can determine. Similarly, you also can get the solidification result and temperature change during the solidification process. Similarly, you can determine the liquid fraction and the porosity that is generated on the component. So I'll take a simple example and I'll demonstrate you how we can define the casting simulation process. So this is a simple calico model. So before showing the simulation setup, just I want to explain you. It has uh, simple pull down menus like geometry and casting. If you go to geometry, it has an option for editing and creating the geometry. And if you go to casting, you have 5-step workflow for casting simulation process. So like initially from designating the casting part and defining the gate and adding the secondary component for the casting, and then you can define the type of casting process. You see, we have high pressure die casting, low pressure die casting, and gravity process, and then you can directly run the simulation. So apart from that, if you want to import the CAD model, yes, you can go to File, Import. There we have an option like for importing the different file formats like CATIA, Unigraphics, ProE, SolidWorks, and so on. Apart from that, you have a translator like Step IGS, Parasolid, and so on. So once you import the CAD model, then you can define the gravity, so direction of gravity. You can select the component. One minute. So first you need to define the gravity. So yeah, once you set the gravity, then you can designate the casting material. So here I am using aluminum. So aluminum 42100 is the material I'm using. And then you need to define the runner system. So I'm selecting the runner system over here. Just right click and assign it. So after defining the runner system, you need to define the gating. So I'm going for gating system. So I'm selecting one of the topmost region over here. So now my gate is assigned. So you can see here cast path, gate, and runner system. After that, you can define the mode. So once you click on secondary components, you have an option to create the mode. So I'm selecting mode over here. And also you have an option to select what type of mold, whether it is green sand or gray iron or copper. So here I'm choosing green sand. Select, and then directly you can go for a run setup. So you can go to gravity. So here we have an option like filling time, spoon height, flow rate, tilt pouring, and so on. So I'm selecting spoon height, and I'm giving the distance as 2 inches. Okay. So then you can run the simulation directly. So once you run the simulation, just I'll show you the output of this. So once you run the simulation, you can see the different result outputs like temperature. You have filling as well as solidification result. So here you can see the temperature change during the filling process. So similarly, you can see the solid fraction and air entrapment, cold shed, and so on. So different velocity. So you can see the velocity pattern, how the velocity changes when it so filling the component and so on. Apart from that, also you can see the air entrapments. You can see here there is an air entrapment over here. Okay. So similarly, in solidification also you can determine the solidification temperature, and also you can determine the porosity on the component. So you can see at present, you can see there is a porosity in the component, and in result legend it shows the percentage of porosity. Porosity that is it is 90% porosity is there in the inside the component. So basically, to avoid the porosity, what we will do, we will define the razors in order to avoid the porosity. I'll show one more result after adding razor. So, So we can add the riser and we can generate the result. But basically, I'll take another model and I'll show you. So this is the model with the riser system. So you can directly add the riser just by clicking secondary component, and you can select riser and you can add the riser by giving the modulus, and then you can extract the result. So you can see now in solidification result, if I go to porosity, you can see here the porosity which is present in the component, casting component has been moved to the riser. So this is how some of the fine tuning work, modifications that we need to do in order to avoid the porosity or cold shirt or what do you say, solid fraction total shrinkage of the volume on the component. So apart from that, you can determine the mold degeneration from the component. So that is also possible. Let us move to next topic. So Inspire Form. So Inspire Form is basically a sheet metal forming simulation tool which helps the design engineer to predict the formability or feasibility study of the sheet metal components. And also user can determine different types of output such as percentage of thinning, percentage of thickening, and wrinkle formation, crack propagation, crack formation, and also spring back effect. So different output user can generate out of this. Apart from that, they can perform blanking and nesting from the one-step forming simulation. So it is a streamlined software for a stamping process. So and you can improve the like you can improve the material usage by using a kind of nesting and blanking tool, and also it improves the productivity with accurate formability analysis and optimize the process through simple and multi-stage virtual trial simulation. So this is the output basically that you will get from the sheet metal forming simulation. So this diagram we call it as formability limit diagram. So this shows the output like thinning, thickening, and the percentage of strain and equivalent stress and displacement that has happened on the component. And also apart from that, you can determine wrinkle formation, and also it shows the failure region, marginal region, safe region, compression zone, and loose metal, and so on. So it is a what five-step workflow, I would say. First, you need to import the CAD geometry, define the forming parameter, run the analysis, and then perform the blanking and nesting. So this is a simple video that will explain you how you can perform the forming simulation. First, we are removing the holes from the component, and then we are removing the cutouts. Okay, after removing the cutouts, we are applying the orientation, forming direction, and then we are defining the binder surface. So after defining the binder surface, you can directly run the simulation. So once you run the simulation, you will get the complete result for the forming, like thinning, thickening, formability limit, the diagram, and so on. And you can use a dynamic callout to see the result dynamically in the output, and also you can simulate the result output, and then you can perform the nesting simulation So using nesting process, you can optimize the material usage basically. That is, the scrap can be reduced very much by using the what you can see, the nesting optimized nesting layout. And this is the application for tryouts. Basically, we call it as incremental analysis, where you can perform kind of trimming analysis, spin back analysis, and also you can perform multi-stage simulation using the sheet metal forming application. So this is the simple video that defines the workflow of multi-stage forming simulation, so where you are defining the material property and then defining the stage and of the simulation. So first I'm selecting the single action, and then we are defining the trimming operation. Post to the trimming operation, we are defining the spring back. So it is a kind of multi-stage simulation process. So once you run the simulation, you will get the output, like the formability of the sheet metal component. Apart from that, you can determine the spring back effect, and also you can determine the tonnage that is required to form this particular component. So this is the formed output. You can see here. You can clearly visualize the tonnage that is required to form the component, and also you can visualize the different outputs uh, from the sheet metal components. So coming to 3D print, so 3D print is Print 3D is basically a tool for 3D printing simulation. So basically, it provides the information where you need to add the support. Thereby, user can minimize the support material, and also it provides the optimized part orientation, and also it reduces the manufacturing defects in the component. So print it right the first time. So after performing the simulation, you can print the model right at the first time. So a simple comparison of the component, like with optimization and without optimization, you can see there is a component on the right side which doesn't require any material support material for 3D printing. So that is also possible through ST Inspire, and it has a setup procedure to perform the simulation. Like first you need to define the path, and then you need to define or configure the printer, and then you need to orient the path, and then you need to generate the printer support and preview the slide, and then directly we can run the thermo mechanical analysis. So from the analysis, user can determine the feasibility of performing the printing simulation. So and so on. Okay. So with this, I came to the conclusion of my presentation. So now we can have a question and answer session.
Good morning, sir.
Yes, yes.
Your presentation was very nice. I have some questions from audience.
Yes.
First one, what is topology optimization?
So basically, topology optimization is a kind of optimization used to determine the optimized material layout. So basically, as a design engineer, they do not know where they have to, in order to reduce the weight of the component, where they have to reduce the material and where they have to retain the material. So this topology optimization will give the optimized material layout that ensures the strength of the component, as well as that reduce the optimize the weight of the structure. So that's where you can use a kind of topology optimization. Yeah.
Okay, sir. The next one, what output we can determine from Inspire form?
So basically, as I said, you can get the formability. limit diagram. So basically, that will give you information about kind of crack formation or during the forming simulation, and also if there is any wrinkle formed on the component, that also we can determine. And it also shows the marginal region and safe region and failed region. Apart from that, you can determine the percentage of thinning and percentage of thickening, and also you can determine the force or the tonnage that is required to form the component, and so on.
Okay, sir. The next one. What are the different type of casting simulation using Inspire Cast?
Yeah. So basically, we can perform almost all the type of casting simulation process, like high pressure die casting, low pressure die casting, and sand casting, investment casting, and metal die casting, and so on. So all the casting simulation process can be performed using Inspire Casting.
Okay, sir. The final one. Why topography optimization is needed?
Okay, so basically the topography optimization is used to improve the stiffness of the component. Basically, and also in order to get the optimized bead pattern. So the software, after defining the design space and also after defining the loads and boundary condition, software will provide you the optimized bead pattern. That is where you need to add the bead, uh, and at what dimension you need to add the beats. So those information you will get from the software in order to improve the stiffness of the component.
Thank you, sir. Next one. Next, we move to the question sessions. Thank vote of thanks session, sir. Thank you so much, sir, for your answer.
Yes. So yeah. Any other questions, sir?
The question session is over, sir. Next,
So,
we move to the vote of thanks.
Okay.
Thank you.
Okay.
Thank
Okay.
you, sir. Thank you.
Okay. So I would like to thank. I would like to thank Francis Xavier Engineering College faculties and the management members, those who arranged this wonderful presentation, webinar session for the students community, and hope whatever I have explained is useful for the students. So students can get back to us regarding any query on the modules that we have presented. So I once again thank you all for your attention and participation. And thank you so much.
Jason, vote of thanks போடல போட்டுடு. நான் தான் உனக்கு தான் இப்போ வந்து மெசேஜ் பண்ணேன்.
Good morning, everyone. I am honored to have the opportunity to give a vote of thanks on this special day. I hope you all enjoyed the session. I liked Mr. Prabhu Sundarajan's speech The content he delivered here was very informative, and the way sir is explained also extraordinary. Thank you very much, sir. We are very thankful to our management, our beloved principal, Dr. V. Velmurugan, sir. My sincere thanks to head of the department, Dr. Joe Patrick, sir, Professor Muthukumar, sir, and all my colleagues and student volunteers, Mr. Jason, for his support. The seminar was made successful only because of the well-wishers, followers, and the participants of this event. A heartfelt thanks to all to make this event success. With this kind message, we move to the end of today's seminar. Thank you all.